Welcome to lecture 59, the final lecture, almost the final technical lecture of this course on muffler acoustics, NPTEL course on muffler acoustics. So, we have covered most of the topics that we intended to do. Obviously, muffler acoustics is a huge area. I will be talking about topics to be covered in an advanced course later on in lecture 60, and I will be summarizing all that we have done in the next lecture, final lecture. But the purpose of this lecture is to give you a very brief introduction on the dissipative or the lined muffler concept, that will be covered later. Right now, we will just give what I will present is just a small introduction. So, for that I will kind of refer to the book on acoustic ducts and mufflers by Munjal, and here what basically there are different models to analyze a lined muffler or dissipative muffler. This is the first time we are just discussing about this thing. So, basically what happens is that if you go to your duct like this, there are different kind of mufflers, lined mufflers. So, suppose you line the boundary of this thing by something like this, by some material. So, when you have such a thing, then you would realize that the waves as they traverse across this thing, across the duct, they are attenuated as they propagate along the duct. So, what happens is that their amplitude decays and significant amount of acoustic power is dissipated in this duct. So, here the main action of this dissipative material is to basically absorb the energy, acoustic energy, or basically convert it into heat as the waves propagate. So, this is a simple lined duct, but you can typically have sort of muffler configuration, lined muffler configuration, something like this. You have a perforated duct, and the inside of this is filled with your rock wool, glass wool, mineral wool, or some kind of a acoustic absorbent material. So, you have this kind of a thing, or else another kind of muffler, that dissipative muffler that usually is encountered is this sort of a thing, which is called a hybrid muffler really. So, you do not allow flow to completely expand freely, like I have been sort of mentioning. So, you have this, okay, you have this kind of a configuration. So, this is what happens here. This is a sudden, the wave front as it enters here, it sees a sudden expansion here. At the same time, the waves that propagate in the annular region, they are also absorbed, they are also interacted upon by the lining here. This is acoustic lining. So, this is called a hybrid muffler because it basically employs the principle of sudden expansion or contraction, and you can also have extensions like I was talking about. So, similar, but this is called a purely dissipative muffler, and these are like lined ducts. Other than that, you also have parallel baffle mufflers, something like we'll soon see the figure. So, the main thing is that we are just going to discuss the different ways to calculate the transmission loss or develop mathematical models, but we can just give you a small introduction, just about 10-15 minutes to get you a feel of this. So, basically there are two models, local reaction and the bulk reaction. So, in the slide that I have presented here, what we do is that the acoustic, all this while if the duct was rigid, normal thing was that you put P by U is equal to Z. If Z tends to infinity, that can happen. If Z is tending to infinity, this can happen only when U or the radial velocity is going to 0. So, that is what we do now. We basically put this condition, the derivative, the radial derivative of the acoustic pressure, or the derivative of the Bessel function is 0 at the boundary, at the radius of the inner radius of the chamber at R naught, to get the rigid wall modes. But if this is not the case, if you have P by U, is equal to Z, where Z can be complex quantity, then you have a line reaction. Okay. So, this is what a local reaction is. So, you evaluate this P by U at Z and get a dispersion relation, solve for that and get back the analytical solution, which will soon browse through that, and develop a transfer matrix which relates stuff from here to here or from here to here, taking into account local reaction or P by U kind of a compliance kind of a thing here. Or otherwise you can also consider wave propagation, within this area, within this region, and that is called bulk reaction. So, there are two models, local reaction, bulk reaction. Bulk reaction is sort of more accurate because it considers wave propagation here, but local reaction is also used quite a lot because of its simplicity. So, what we will do is that we will just go through that in the next 10 minutes. So, rectangular duct, you have this momentum equation, Euler, and you get the particle velocities along the x and y direction. And now, when you have this P, so you employ this impedance condition, P by Ux is equal to ZWx and P by Uy is equal to ZWy. And now this impedance, like I said, it is not infinity. If it is infinity, then Ux has to be 0, Uy has to be 0. Similarly, for the circular duct, for a circular duct we do not have, where is it, I guess a bit down. So, this is the modal solution and this is the Euler equation that we get, and if UR is 0, then of course your ZW tends to infinity, but that is not the case for line duct or a compliant duct, so you have this condition that minus j omega rho naught Jm Kr Mn, where this Mn is the mnth mode and ZW can be a complex quantity in general, which depends on the properties of the absorbent material. So, you have this regular modal solution, which is solution of the Helmholtz equation. From the momentum equation derive the expression of the particle velocity, radial particle velocity, and get the expression for impedance, where this is the derivative, and technically as usual it will give you infinite roots, just like we had infinite roots for the rigid wall case. For a given order M, there are the set of ordered roots, because it belongs to the properties of Sturm-Liouville problem. But similarly here also you have, for a given M, you have a set of ordered roots, and once you get ZW expression, you can find out these roots and substitute back in the expression for the particle velocity as well as the pressure to get the field, acoustic pressure field in a line duct. Okay. And and this is the dispersion relation that is usually considered. And one thing that is there is that for a line duct or a dissipative duct, the plane wave mode does not really exist, because dissipative duct means that the pressure, even for the lowest order mode, we talk about the least attenuated mode or the lowest order mode, the pressure variation will be there across the cross section. So, the plane wave mode does not exist. So, and it so happens if the duct is heavily damped, if there is a significant damping, even the first few modes can help us get a good estimation of the transmission loss in the low frequencies at least. And then there are bulk reaction, rectangular duct with a bulk reaction model, where you consider wave propagation within this thing also. Similarly, bulk reaction model is also given in for a circular duct, where you have this expressions for the pressure in the airway and that in the annular cavity. Okay. And then you get this basically your compatibility sort of conditions, and then we get the dispersion relation for this kind of a thing. And finally, the whole idea of doing a bulk reaction is to simultaneously consider wave propagation in this domain as well as this domain, a coupled kind of analysis. So, that is naturally expected to be more accurate, and one can find out the transfer matrix. Let me go to the chapter 6, I reckon, of the muffler acoustics book, duct acoustics of ducts and mufflers by Munjal, where practical expressions are sort of presented for measuring the transmission or obtaining the transmission loss. So, I will go for the case of a circular duct only for the lack of time, so I will, and that too with a moving medium. So, in moving medium you have Kz plus Kz minus, like we have been discussing, okay, and you have this model. So, we get this constants, and then from the dispersion relation we can find out Kz Mn plus minus for a given Kr. Kr can be found out using solving the dispersion relation as we obtained previously also for a given Zm. Zm has to be known for a perforated impedance expression has to be known. The impedance expression for a line duct which is backed by a perforated sheet has to be obtained, which and we will soon see the expressions for that. And once we obtain P and U, we can find out the transfer matrix for a dissipative duct. So, we will talk about only the least attenuated mode, M is equal to 0, N is equal to 0, and drop the higher order modes. And let us worry about the circular duct only. So, for a circular duct it will be like this. ZW is related to the least attenuated mode is given by is obtained, the roots are obtained, Kr is obtained by solving this equation numerically, say using some Newton-Raphson scheme or things like that. Particle velocity is obtained, and then the mass velocity is obtained, and from these relations 6.45 velocity and actually 6.48 and 6.49, once we get that, we can obtain the transfer matrix parameters, where we relate the upstream variable to the downstream variable, incorporating only the least order mode. So, the effect of all the information pertaining to the dissipative or the line duct is stored already in KZs, which is KZ is related to Kr using the the dispersion relation Kz square plus Kr square is equal to K naught square. Okay. So, and Kr itself is found out using this equation. Okay. So, you can just set M is equal to 0 and find out things. You can solve for Kr, and then you can find out Kz is root over K naught square minus Kr square to get the transfer matrix for an infinite length duct, or not assuming any reflections. So, this can be related to that, and there are expressions for the z omega, which is basically given by y in terms of yw and kw, that is the characteristic impedance of the material and the wave number, and they are well established formulas for obtaining that, and they are given in Wer's paper, Beranek and Wer. So, it's given in these non-dimensional expressions, which are obtained experimentally or through lot of simulations. Then there are bunch of expressions given in Salamet's paper also. So, once we know it for a given material, we can find out the ZW value and solve for that. So, the transmission loss for such a thing, for a this kind of a muffler is basically it can be thought of something like 8.68, that is simple algebraic simplification time alpha naught, where alpha naught is the pressure attenuation constant for a least order mode. And for the muffler that I showed here, this one, the transmission loss would actually sort of look like is given here. Low frequencies are the dissipative mufflers are sort of less effective at low frequencies and more effective towards the higher frequency. So, you typically combine reactive muffler with hybrid muffler, reactive muffler with your dissipative thing. You typically put that dissipative element in the downstream of the reactive elements and control the attenuation after the first cut on frequency where higher order modes start. And there is a difference between local reaction and bulk reaction. So, these are the things for a circular duct with different values of D and H, certain parametric values. And then there are things like, I will quickly go to parallel baffle mufflers, where what happens here, that in the flow passage, the flow is split into number of parts, number of segments depending upon baffles or which are lined baffles, and as the waves go through these baffles, they are attenuated. And typically in an engineering, purely from an engineering perspective, what happens is that have a look at this graph. So, this is the graph where we can probably do some engineering based calculation. So, H is the difference, H is nothing but the passage 2 times 2H is the passage length between the two successive baffles. W W is the overall width and is much greater than the thickness of the and it is much greater than the passage length, and D is the diameter, the thickness of the baffle. Okay. So, and another parameter, one very important parameter in such a context is basically the attenuation produced per unit length H, per unit length H of the baffle. This is called the specific attenuation. And so, once we know the length, overall length or attenuation produced per unit thickness of the baffle. So, once we know it, we can multiply this by the overall length and find out the total attenuation produced over a length L once we know the specific attenuation for a thickness equal to h, where h is the half the transverse dimension of the flow passage as I was mentioning. So, once we know TLH, we can find out for any length TL. So, how do we find out once we are given different h values and different d values? So, from these charts, so once we know what is d value for a perforated parallel baffle muffler. So, parallel baffle muffler as it looks like here, this is the thickness of the perforated the thick baffle, then 2h is the twice is the thickness of the air passages through air goes through the passages where I am pointing my mouse cursor here, and this is the absorbent material of each of thickness d. Okay. So, we look at the specific transmission loss for a given d by h, say for a d by h 5, if the ratio of the thickness of the baffle dissipative baffle sheet to the passage distance is 5. Okay. So, that is that is basically this curve, and it is plotted versus non-dimensional frequencies 2h passage length f by c naught sound speed. Okay. So, f by c naught is the frequency by sound speed. So, basically by second, and this is meter by second, and this is c naught. So, this is also meter by second. So, eta is the non-dimensional frequencies. Apologies for the small confusion. So, if we consider d by h 5 and if we take a particular non-dimensional frequency say 0.1, okay, and we know the value of if we know the value of h, okay, and d, so and d by h we know that the dimensions are that d by h is equal to 5 or something like that. So, we consider that curve, and for a given non-dimensional value we find out the specific attenuation and multiply that with the length, overall length that is required of the muffler to get the attenuation at that frequency, okay, from these non-dimensional curves. So, suppose if it is between 5 and 1, so the 5 or 2 or something like that. So, we interpolate between, for a given frequency we can interpolate between this value and this value to get the specific TLH and multiply with the length. So, using such a thing you can find out the from an engineering perspective what will be the attenuation for a parallel baffle muffler. So, these are the normal attenuation curves for this thing. Now, all this parallel baffle muffler concept and lined chambers, plenum chambers, line ducts, all these things have to be considered in a much greater detail more formally, because this is not really something that I have done justice to because of lack of time. What we really need to do in the next course is that consider at length dissipative mufflers, hybrid mufflers, and combination of these dissipative mufflers with this reactive mufflers to control especially high frequency noise. So, and obviously one challenge is always there to design or get an absorbent material which can control low frequencies as well. So, basically the idea is that we will cover a lot of topics in the next advanced course, but for now I will just sort of stop here, and in the next class we will summarize all that has been done in the course so far. So, I hope you really like the course, and with this thing it brings end to the technical presentation of the course. So, hope to see you very soon in the future, and please send your feedbacks. So, thanks a lot for attending. I am very grateful for all of you guys who have taken the course, and do send your feedback and do complete the assignments, and hopefully people who are registered for the exam should do well in the exam, and thanks a lot.